f of x is equal to 1 over x. We all know what this thing looks like, right? It looks like this, doesn't it? Okay. Well, then obvious question. See, limit exists everywhere. For example, if you say limit of f of x as x approaching 1, I mean, that's 1, isn't it? But that's a very uninteresting limit. What we want to investigate, of course, is this. Well, let's do this. We're going to do 0 as well, but we'll do infinity first. You know the answer to this? What is this limit? And we can also say limit of, and since f of x is same as 1 over x, we can just put that in, and that, of course, is equal to, according to last year, that's 0, right? Now, do you have issues with this answer? Even if it's x is trillion, I know that's not infinity, but 1 over trillion is not 0. That's what asymptotic behavior is. This is asymptotic, meaning it never touches it. So what do you mean by 0? What is the definition of your 0, or what is your definition of equal to? I mean, we have to investigate one of this. I know you just accepted it, or maybe memorized it, that's what it is, but really, do you know what you're talking about? And this ties into tomorrow's epsilon delta proof, which is very, very, very important. So let's get to, this is my side of the board. See, in the classroom, I have the big board, so I can go to the side and do these things, but hey, let's do it here. 0.9 repeating. Are they equal or are they not equal? How many of you think they're equal? How many of you think they're not equal? How many of you are able to think? Oh, that explains everything now, right? Too late. Okay, those of you who don't think, okay, here's elementary. I went to a fabulous elementary school in Korea. And then they try to convince me that these are equal by doing such a thing. Let's subtract two numbers, and then you get 0.000000 dot 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 forever. Oh yeah, see, 1 minus 0.9 repeating is equal to 0, so these two must be same. Well, now aren't you convinced more than ever they are not equal now? Once you see like one, there's like one somewhere, like how far, like very far that way, but there is one, infinitely far. This bugs you now, doesn't it? However, those of you who don't think they are equal, for some reason are a lot more willing to accept this one. Well, what happens if you multiply both sides of this equation by 3? And you get this, so they are the same thing. So either they are both equal or both not equal. Which way is it? Well, that really depends on what your definition of equality is. Oh my God, here we go again, right? The definition, different definition of, yeah, it's like math. Unfortunately, in math, this equal sign is being used loosely. Strictly speaking, these two numbers are not exactly equal. I wish they used the arrow here. This number is infinitely close to that number. How close? Well, forever 0. What that is, I want that kind of equal. You know what I'm saying? Okay. It's more like, let's talk about the laws of thermodynamics. Oh, you guys took chemistry, right? So you remember forgetting laws of thermodynamics? I happen to know these things because I'm a science major. I have a double major degree with physics and math. Okay. First law of thermodynamics, what was it? Energy is conserved. Oh, come on, people. How do you forget conservation of energy? Okay, number 2, entropy. Entropy is in a spontaneous reaction. Entropy is always increasing, right? Well, at least this has to be 0. It doesn't go the other way. Room always gets messier, even if you do nothing. What's the third one? Zero energy cannot be achieved. Another way of saying that is you cannot get to absolute zero. Remember forgetting that one? My chem professor actually put that third one a little differently. First two are the same, but he has 4 laws of thermodynamics. Number 3, zero energy can only be achieved at absolute zero, is how he said it. Otherwise, it can't be achieved because no matter how cold it is, there are still vibrations between the molecules, so that there's a kinetic energy. That's what temperature is, by the way. Vibration of the molecules, kinetic energy within the molecule. You get it? So only if you freeze it down to absolute zero, then you can achieve zero energy. Guess what number 4 says then? You cannot get to absolute zero. What? Why would you want to do such a thing, right? That's why your chem teacher said that's a third law of thermodynamics. But my professor, actually, that's like profound reason. Although you cannot get to absolute zero, you can get to absolute zero as close as you want to. That is this concept, these zeros, right? I mean, there is a 1, but you can push that 1 as far as you want it to. That is concept of limit. You get it? So limit, so let's get it together, because if you don't understand this right now, then this will forever be confusing. Limit meaning, see, we used to, at least we don't use equal sign here, right? This number, it means x is not equal to 1 and that function is not equal to 1 either. So when we say equal to in limit, it's not equal to. I so wish they used arrow right there. The way we interpret this statement is, as x approaches infinity, f of x approaches 0 is how we, and as close as you want it. But it's not equal to. That is the definition of limit. Tomorrow I'm going to use the epsilon delta, real definition of limit, and it's a heavy stuff. But for now, okay? So then we can continue here. Then, of course, limit of f of x as x approaching 0. Wow. Denominator is approaching 0 now, isn't it? So something over 0. Well, it depends on which side you're approaching, right? The right-hand side. What's the answer? Infinity, right? And then, because if you approach 0 from the right-hand side, this side shoots up, right? And the other side goes down to negative infinity. So the limit of f of x as x approaching 0 from the negative and left-hand side is negative infinity. Okay, of course, they are all both limit doesn't exist, non-existing limit. Technical word for this is called divergent limit. Limits diverge, but what kind of divergence are they? They are called infinite. That's why and that's a little different than oscillation and the other stuff. So that's why we tend to write infinities down, but we cannot combine the two, right? So we say, then limit of f of x as x approaching 0 does not exist. How about that? You get it? Okay, moving on. My next example is this. G of x is equal to x squared minus 1 over x minus 1. Do you know what this thing looks like? What is this thing? Oh my God. Okay. If you factor and cancel, is it same as x plus 1? No, it's not. Oh no, what are you doing? No, they are not saying what? They can. Okay, if you write it like this, it's understood by everybody in mathematics. X is not equal to 1 because you cannot divide by 0. Get it? By the way, did anybody tell you that, oh, later when you grow up and finally take calculus, then you learn how to divide by 0? Okay, that person did not know what he was talking about. No, he's like, I have a degree in math and I'm pretty sure you cannot divide by 0 ever. But once you cancel this, they are talking about this limit stuff, okay? Once you cancel, you lost that information. So you have to write this thing in. Now they are the same thing. And this is what creates so-called the hole. Otherwise, it's a line, right? Now, let's talk about this. If you try to plug in 1, the numerator becomes 1 squared minus 1, 0. Denominator becomes 1. So, 0. So 0 divided by 0. What's 0 over 0? Do they cancel and give you 1? No, by looking at it, what's the limit? It's 2, isn't it? These type of things can turn out to be anything between positive and negative infinity. In fact, 0 over 0 type of limit is what derivative is all about. Okay, we're going to get to that. It's a big deal in calculus. But for now, baby steps first, right? So this thingy, if you say limit of g of x as x approaching 1 from the right-hand side, that means you're approaching that point from there. And that, of course, is equal to 2. And then limit of g of x as x approaching 1 from the left-hand side, that is same as approaching it that way, and that's equal to 2. And when these two agree with each other, the left limit and right limit agree with each other, then you can say x, limit of x approaching 1, no plus, no minus sign of g of x is equal to 2. So left limit and right limit must agree in order for the limit to exist. You get it? Now, you notice there still is a hole there, but that's okay. Now, a little technique of doing this instead of doing it that way, of course, is limit of g of x, x approaching 1, no plus, no minus sign, and watch this. Just substitute it with x plus 1. Wait a minute, then do I have to write this limitation down? Because after all, these two are not equal. So do I have to write that x is not equal to n right here? What do you say? No, you don't. Do you know why? Because I said earlier, when we say limit x approaching 1, meaning x is not equal to 1. You get it? You get it? So we don't have to write it. As long as they are not equal to, this is 2. Okay, that really means g of x is not equal to 2. See, there's a hole. It'll never become 2. Right? Nevertheless, g of 1 does not exist. Limit exists. So here's a layman's concept of a limit. You see my fingers? You squeeze it. It's tight. You know, those of you who took bio, you know there's a gap between my fingers, right? That's kind of like what limit is. If you can squeeze it from both sides, I mean, this is tight enough that no water or air molecule will pass through, but there is a gap. That's kind of what limit is. You get it? It's like the original case here, this, like that gap will get so tight that nothing will pass through, but they are not equal to, there is a gap. Kind of get what limit is? Okay, third example, because I'm kind of trying to get to that proof part. H of x. You guys know what this looks like? Oh, you don't know? Okay, well then. I guess we'll learn what that looks like. Okay. Do you remember we can put this as a piecewise function? That's what gives you v. We can split absolute value as a piecewise function, and then we can divide d by x, where this is equal to 1, this is equal to negative 1. You know what I'm saying? 1, negative 1, constant functions. Okay, having said that, let's take a limit. Guess where I'm going to take the limit? X approaching 0, of course, right? 0, because this, if you put 0, that's like absolute value of 0 over 0. Ah, 0 over 0, huh? Calculus, that's most interesting one. Calculus is all about that kind of limit. So, but in this case, since it's a piecewise function and x is technically a little positive, so we take this piece, say, and it's constant function. That means it's approaching 1 from the right-hand side, right there. And limit of x approaching 0 from the left-hand side. And that is same as limit x approaching 0 from the left-hand side. Now we take this piece, say, and that's, of course, -1. From these two, we can conclude that limit of, let's say, h of x, x approaching 0 does not exist. You get it? So to summarize it all, limit exists at a continuity or at a hole. If there's any other kind of discontinuity, limit doesn't exist. Only discontinuity, the limit still exists, is at a hole. Get it? This case, the hole is the only case. How about that? Does that give you the concept of limit? Okay, period ends at, 10 minutes. Maybe I'll make it. We'll see. The next example is this. Then what is the limit of, and guess what data will approach? 0, of course, right? What is the limit of that? Still 0 over 0 now, isn't it? Have you seen this in pre-calc book? Okay, graphically we can figure it out. This is a graph. Okay, it really looks like this, but I rescaled it. And you notice there's a hole right there because denominator becomes 0, so it's not a continuity. But looking at this, and I'm gonna save this to the notes. Paste it. Oh, that's big. Looking at this, and there's like, all right, let's exaggerate it. So right-hand side, it approaches 1. Left-hand side, it approaches 1. So it looks like this is equal to 1, graphically. You know what I'm saying? Okay, how do we prove it? Let's prove this, okay? For that, I need another graphics, which is this, okay? This is a unit circle, and I have a few triangles. Okay, I'm gonna copy this and put it here. Once again, this is big. Okay. No, actually. Now, do you see that area of triangle OPA, that triangle right there, right, is less than the area of sector OPA by that much? Do you agree? Okay. Now, and that area of the sector, of course, is less than area of triangle, area of triangle OTA by that much. OTA is that big triangle. So far, so good. So we have three-way inequality. Good, good, good. Now, what's the area of a triangle? 1/2 times base. So this base sure looks like 1. Why is that? Because it's a unit circle. You get it? 1/2 times 1 times height. How much is this height right there? Do you see this is sine theta? And a unit circle is a cosine theta, sine theta. That coordinate xy is cosine sine. You know what I'm saying? Okay, so we have sine theta. Do you remember the area of the sector formula? Oh boy. Area of a sector. Do you remember 1/2 r squared theta? Somebody remind me to prove this later, or if we have time left over, then I will prove it, but I'm running against clock here, okay? So this is 1/2 times 1 squared times theta, right? Because our radius, this is unit circle, once again, radius is 1. Okay, now, and this is 1/2 times 1, the base is still 1. What do you suppose that side is? This side happens to be tangent theta. What? Really? Do you believe it? That one I will actually bother to prove it here. Say tangent theta is opposite over adjacent, right? So we'll call this thing h for now. So that is h over adjacent 1. You see, h is equal to tangent theta. You know what I'm saying? Do you ever wonder why tangent function is called tangent? Because tangent in geometry was tangent now, wasn't it? This is part of the tangent segment. This is what we call tangent segment in geometry. If you just throw that, remember this? These are tangent segments. Ah, tangent segment, that's why we call this thing tangent. You get it? My God, they had a reason. Then what the hell is secant? What is a secant from geometry? That's a secant, right? Why is the reciprocal of sine cosecant, and why is the reciprocal of cosine secant? Shouldn't that be the other way around? Do you ever wonder? Okay, let's just investigate what that side is, right? Somebody give me a letter. Okay, Z. Okay, so Z over 1, right? Hypotenuse over adjacent. What do you call that? Is that secant? Yeah, it is, right? That's reciprocal. You see, Z is equal to secant. So this thingy happens to be literally was secant. That's why reciprocal of cosine is secant. It's part of that. See, this thing goes through. So it's secant is all the way through here and part of that secant. You get it? Oh my God, you remember secant segment? Yeah, okay. That's a little side note. So this height right here is tangent theta. So far so good. Multiply everything by 2, so we can write sine theta, theta, and this tangent, of course, is sine theta over cosine theta, right? Divide everything by, and this is in first quadrant, so this is a right limit that I'm trying to figure out. Left limit, you guys can try it. Divide everything by sine theta. Okay, you do know that these are all positive numbers because we are in the first quadrant now, right? Flip everything. If you flip fractions, positive fractions, then do the direction of the inequalities also flip? Yes. But then, oh wow, why does this thing in the middle look so familiar? That's this thingy that we are trying to find. I'm building that thing in the middle of this three-way inequality. It's being sandwiched. So now we take limit, x of theta approaching 0, limit of theta approaching 0, and the limit of theta approaching 0. You get it? Somebody tell me what this limit on the left-hand side is. And somebody else tell me what the limit on the right-hand side is. This is 1, right? What's the limit on the right-hand side? Cosine 0. What's cosine 0? 1. What's the only conclusion you can draw from this? This must be 1 as well. Oh my God, huh? So the value you want to know, unknown limit value, is being squeezed between the two known limit, and these two will give you the same answer. So you have to build this thing. This is known as a squeeze theorem. And regretfully, in your textbook, they call this sandwich theorem. I didn't come up with that name. Squeeze theorem is so much better. Graphically, we can see that. So go back here. Okay, I'm going to graph a couple of other functions that's squeezing it. Cosine x looks like that. And then if I graph sine x, cosine x 1 looks like that. So let's watch this, right? Our function cosine is below 1 and above. This our function sine x over x is below 1 above cosine. You get it? And it has to go through that. It's literally being squeezed through that point where there's a hole. So that limit must be 1 is graphically what it looks like. You get it? Many times, I mean, you want to say, maybe it's at the ratio of these two, right? But many times in math, you can, hold on, I'm going to leave little space here, limit of sine 4x over 4x. Wouldn't it be nice if it's like that? And that limit is equal to 1 now, isn't it? Because 4x is theta now. And then I'm going to do this. Sine 3x and 3x. How about that? Because see, limit as x approaches 0, limit kind of is a limit of this thingy times limit of that thingy, isn't it? Limit just means that whenever you see x and then let it approach 0. Right? But this is not exactly same as what we have here. But many times in math, you can write down whatever the hell you want to. Then you can adjust it. So if I write it like this, let's see which one cancels. This x is going to cancel, so that's fine. And then we have that 3 here, so that's fine. So only thing that is screwing us up is this 4, isn't it? So why don't we just put 4 there? Then it's going to cancel. So now we have exactly the same thing. However, now if we take limit, and this is kind of my notation of taking limit, and you can use it too, instead of rewriting, this becomes 1, this becomes 1. You get it? So what we have is 4 times 1 times 1, 4. How about that? That was beautiful now, wasn't it? You see, that was a nice trick. Okay, now I'm going to do this then. This one is not as obvious, but we'll think conceptually. It's a limit of this versus limit of this, right? This thing approaches 0, as we know, right? This thing, we don't know, right? But it oscillates between 1 and -1. So this thing is at most 1 and at least -1, isn't it? It's some kind of finite number. So what is 0 times some kind of finite number? It's 0. However, that's like nice to feel it, right? We can all feel it, but we have to justify our feelings. How do we justify it if you have a test question like this and then justify your answer? This is how you do it. Ready? Squeeze theorem that I taught you yesterday comes in handy. So sine x, then this is how you use it. You always start with 2 known quantity on either side, and then some unknown quantity, and you're going to build this unknown quantity in the middle. And then I multiply x squared everywhere. X squared. Good. Now I take limit, limit, limit. It's just a lot of writing.
Wait, why is there a sin x on the third one?
Oh my God, because I screwed up. Nice catch. Oh, you don't know this about, here's the beginning of the semester. I usually make on average of 2 mistakes per class. And it's your job to catch it. I'm just trying to see if you're paying any attention or not. You get it? Okay. Now, then as you can see, this is 0 and this, oh, maybe I can do this, right? Copy and paste. Oh, it worked beautifully, right? Oh, one of the advantages of distance learning, the paradise, is that I can be a little lazier and don't write it on the board. Okay, so only way we can conclude that to be true is this thingy, you see how convenient that was, is equal to 0 as well. You get it? Any other questions?
For 28, how do you graph it? Like, do you just plug in points, or like, how do you graph it without just plugging in points?
Oh no, this thing like requires graphic calculator.
Okay.
Yeah, that's humanly, I wouldn't expect you to be. I expect a lot, but not something like this. This is like super ability. Okay, Kara.
For on tests, are we going to be able to use a graphing calculator as well for graphing problems, or?
There are calculator tests and there are non-calculator tests.
Okay.
Okay. Any other question?
Yeah, for number 28, so like how does sine 4x over x just cancel to 1?
Yeah, let me do that on the side. Limit, it does not let me change the color, huh? Okay, whatever. Limit sine 4x over 4x, this part, right?
Yeah.
Okay. Watch this. Let theta be 4x, right? And this is the same as, and now as x approaches 0, theta approaches 0, right?
Yeah.
Do you recognize this one?
Yeah. Okay, so that one makes sense, but how about the 3x over sine? Is that the same thing?
It's just a reciprocal of 1 now, isn't it?
Okay. Yeah.
Right, okay. I know sometimes like, oh, duh, right? That happens a lot in this subject. Trust me, I've been there and done that too. Okay, wait, somebody's waiting in the lobby. Somebody got cut off. Wait, and gave up. What happened? Okay, hopefully. Okay, Sasha.
Wait, why does the limit of theta to 0 of sine theta over theta equal 1?
That's a long story. Previous lesson, squeeze theorem. Yeah, yesterday's lesson, like 2 days ago. Let me try to find it. Of course, having not so organized. What is this? This computer. Was it here? Yeah, this thing. This long squeeze theorem right there. Okay. Okay. Alrighty. Any other questions? Okay.